Good evening students. I am going to start the class. Today class is very important and whether my voice clear or not you can tell me. Okay. And today class is the based on capacitors. Okay. If you have any doubt you write in the chat box. Right students, I am going to start. Clear, baby Mato said Suraj and right, okay. Voice is clear. Let us start the class. If you have any doubt while teaching, you write in the chat box. Okay? Right. The first of all, I am going to start the concept that is potential due to potential at a point potential at a point due to charged conducting sphere. Okay, based on this derivation is not required for us. You should remember the formulas. Okay, potential due to charged conducting sphere. For example, this is a conducting sphere. We can consider this is a conducting sphere. What is the meaning of conducting sphere? For example, if it is a metal sphere, it is said to be conducting sphere. The charge will resides on the surface of conducting sphere. This is the charge. Okay, the q charge will be there on the conductor. Okay, and the radius of the sphere we can consider as capital R. I want the potential due to this charged conductor. What is q? Q is the charge. Q is the charge on conducting sphere. Q is the charge on conducting sphere. Okay, and capital R is the radius of the sphere. Radius of sphere. I want the potential due to sphere. First of all, I want the potential at outside. Okay, I want the potential at outside of the conducting sphere. Outside means I want to find out the potential at a point. That point distance is greater than the radius of the sphere. Okay, right, let us see here. I want to find out the potential at this point. Okay, this point is at outside of the conducting sphere, and that point distance we can take as the smaller is the distance of the point where I want to find out the potential, right? And then how to find out that potential at outside? Okay, okay, if just it was, you can remember the potential formula. Okay, for example, if the whole charge resides at a single point, then from that at a r distance, what is the formula for the potential? Do you know? Right, potential formula due to point charge, that is 1 by 4 pi epsilon naught into q by r. That formula we will use. Right, outside the potential formula is 1 by 4 pi epsilon naught into q by small r. What is smaller is what? Smaller is the distance at the point where you want to find out the potential. Okay, right. The second point, I want the potential on surface of conductor. On surface of conducting sphere. Okay, I want the potential on surface of conducting sphere means then we have to take smaller is equal to capital R, we have to take. Okay, smaller is equal to capital R. Why? What is smaller actually? Smaller is the distance at the point where you want to find out the potential. Okay, right. Then for the purpose we have to take this one like this. You see here, we can take this as a sphere. This is a sphere, and the sphere conduct, its derivation is not required for us. Okay, its derivation also there, but it is not required. The formula you should remember, that's why I am telling the formula. Okay, this is the q charge, and the capital R is the radius of the sphere. Then smaller is the distance where I want to find out the potential. At this location I want to find out the potential, that is the potential on surface, how much. Right, the potential on surface means we have to write in above formula smaller is equal to capital R, right, because on surface means on surface distance, right, that is equal to capital R. Then we write potential on surface formula as 1 by 4 pi epsilon naught into q by capital R. Okay, right. Next, third point. Third point is that I want to find out the potential at a point inside the conducting sphere. What is the potential at a point inside the conducting sphere? Inside the conducting sphere. Okay, charged conducting sphere it is. And inside I want the potential. That inside means the distance is less than radius. Okay, right. Then here let us consider this is a charged conducting sphere, and the charge on that is, we can consider as the small q. Okay, the charge already we consider it as a small q, and the radius of the sphere we are considering as the capital R. And then we have to find out the potential at a particular point. That point here. Okay, here I want to find out the potential, right? V is equal to how much, and then the potential inside formula, that is equal to, you should remember, the potential inside equal to potential on surface, right? Inside at any point the potential is constant. Potential inside at any point is constant, that is equal to potential on surface. That means potential inside equal to potential on surface, right? And that formula is 1 by 4 pi epsilon naught into q by 1 by 4 pi epsilon naught into q by capital R. These formulas you should remember, and this we will use in future, right, in the capacitors topic. Okay, you should remember that potential outside, what is the formula for the conducting sphere, right? Outside from the q charge at a distance r, potential outside formula is 1 by 4 pi epsilon naught q by smaller outside distance we have to take. On surface means on surface distance we have to take, that is equal to radius of the sphere. And inside means inside at any point the potential is remains constant, that is equal to potential on surface. This is the formula for the potential on surface. Inside potential equal to on surface potential, right? Okay, these are the formulas that you should remember, and it is very important. Okay, just you remember the formulas. These formulas we will use in the future to learn some other concepts. Okay, right. Now let us go for the concept of capacitors. The capacitors concept is the very important in this chapter. In the previous chapter, electric charges and fields, in the first chapter, the most important one is Gauss law and its applications, right? Gauss law 3 applications are there. Out of that, one you will get in the board exam. Then in this, the capacitor concept is very important. Now first of all, I am going to start the capacitor. What is a capacitor, right? You learned the capacitor, I think, the term. Anybody knows what is capacitor? Write in chat box. If you know what is capacitor, then you write in the chat box. Right, capacitor is a device. It is a device. Okay, at any many in computers, right? In televisions, in old televisions, right? There are so many capacitors they are using. Even we can use the capacitor for our fan also, right? Capacitor is what? Capacitor is a device. Capacitor is a device. A device used to a device used to store the charge. A device used to store the charge. A device used to store the charge is called as capacitor. Capacitor is a device that can store the charge, used to store the large amount of charge. Large amount of charge at low potential. Okay, at a low potential. This is the definition of the capacitor. Simply, the capacitor is a device. It is used to store the charge. It can store the charge. Right, a device used to store the large amount of charge at low potential or at less potential is called as the capacitor. Right, what is the symbol of the capacitor? Where you will use the capacitor, right? And the capacitors are used to convert the alternating current into direct current in that devices. In rectifiers we will use, and in starters, for example, to start a motor we use the capacitor. Without capacitor the motor cannot start. The fan also have the motor, the coil, to rotate that coil, the capacitor at the initial stage it will be useful. And here the capacitor symbol I want to know, right? What is the symbol of the capacitor? Right, this is the, okay, capacitor symbol. Capacitor has the two plates. Okay, and here for example on this plate if it plus q charge stored, on this plate minus q charge is stored. Then the capacitance, this capacitor has some capacity to store the charge. That capacity is called as the capacitance. It is denoted with c. C is the capacity of a capacitor. For example, we have a container. Okay, we have a bucket. Okay, we have a bucket to store the water. Then it can store 10-liter capacity, right? 100-liter capacity. We have a drum, big bucket. It can store the 100-liter water. That every object, for example, every container has some capacity. Like that, this capacitor also have the capacity to store the charge. That capacity denoted with the C, right? If it can store more amount of charge, its capacity is more. If it stores the less amount of charge, its capacity is less. This is the symbol of capacitor. Okay, this is the constant capacitor. That means its capacity not changes. Okay, if the capacity, generally the battery symbol also same will be there, but one big line and other one is a small line. But in the capacitor two lines are at equal length. Okay, and if you have the variable capacitor means its capacitance is changes. Capacitor also used in many ways. Okay, it is the symbol of variable capacitor. Variable capacitor. Okay, right. And now for example I am taking some, this is a conducting sphere. Okay, this is a conducting sphere. On this I am giving some charge for this sphere. Slowly I am increasing the charge on the sphere. Slowly I am increasing the charge on the sphere. For example, the charge on the sphere at any instant I am considering as the q. Okay, and the radius we can consider as the small r, and the potential on the surface we can consider as v. And we know potential on surface of conducting sphere, right? What is the formula for the potential on surface of conducting sphere? We know potential on surface of conducting sphere, right? What is the potential formula? The potential formula is v is equal to 1 by 4 pi epsilon naught into q by r. Is it right? Q by r. This is the formula for the potential on surface. And here if you increase the charge, then its potential also increases. From this we can say that the charge stored at any instant is directly proportional to the potential. Then when the proportionality is removed, okay, if you will store more charge, its potential will be increases. Then when the proportionality is removed, we will get a constant. That constant is called as the c. Okay, That C is a proportionality constant. Its name is the capacitance or the capacity. Capacitance or the capacity of a capacitor. Okay, capacitor means device. Capacitance means property. Okay, for example, bucket is a device, and bucket capacity means how many liters it can store. Okay, for example, this is a bucket. This bucket, how many liters it can store, that is the capacity, right? Similarly, the capacitor has the capacity to store the charge. For example, uh, generally in the bikes we will use the light. That means instead of using battery, I am using the capacitor. The capacitor cost is only 20-30 rupees, but the battery cost is the nearly 700-800 rupees it is there. Okay, the capacitor can be used to store the charge. Okay, that charge can be used. Okay, right. And the next one is the I am going to write the capacitance definition, right? Till now, if you have any doubt, you write in the chat box. Okay, whatever that I am telling, is it clear, students? Okay, now let us see the capacitance definition. I want capacitance. What is a capacitance and what is its unit? Then it was very simple. The capacitance is the one definition is the ability of a capacitor to store the charge. The ability or the capacity, right? The ability of a capacitor, to store the charge. The ability of a capacitor to store the charge is called as capacitance. This is the capacitance. Capacitance is the ability of a capacitor to store the charge. And there is another definition is also there. The capacitance formula is the ratio between amount of charge to the potential. Amount of charge to the potential is called as the ratio between amount of charge to the potential is called as capacitance. Okay, right. Previously I told the formula for the capacitance, right? What is the capacitance formula? Just now here you see Q is equal to CV. The amount of charge stored on the capacitor will be equal to C into V. From that we can write the C formula. Yes, you know Q is equal to CV. Then from that the capacitance formula C is equal to be write as Q by V. Okay, right. Generally the capacitance formula is appearing like the ratio between the charge and potential, but the capacitance is independent of charge and potential. Capacitance does not depends upon the charge and potential, because when the charge increases, the potential also increases. Okay, but the capacity not changes. You know that charge is proportional to potential. When charge increases, potential increases. Then the ratio will be remains constant. When charge increases, the potential increases. The ratio is constant, right? Okay, this is the definition of the capacitance. And what is the unit of the capacitance? SI unit. SI unit is the farad. Okay, farad is the unit of the capacitance. Okay, small capacitance we can write as small capacitance we can measure like this. Small capacitance we can write as millifarad, microfarad, nanofarad, picofarad, like this. Okay, 1 millifarad means that is 10 to the power of minus 3 farads. 1 microfarad means 10 to the power of minus 6 farads. 1 nanofarad means 10 to the power of minus 9 farads. And 1 picofarad means 10 to the power of minus 12 farads. Like this, we can write the small units of farad. Okay, we can also write definition of the farad also we can write. How we can write the definition of the farad? Okay, by using the capacitance formula we write like this. Okay, farad definition if you want to write, we know formulas capacitance C is equal to Q by V. For example, I am taking that if at 1 volt potential, if V is equal to 1 volt, okay, potential is 1 volt, and the amount of charge stored is 1 coulomb, then what about the capacitance? Capacitance is C is equal to Q by V. We write the Q as 1 coulomb and V as 1 volt, then C is equal to, we will get as 1 farad. That means if, I think I am facing the network problem. Due to network problem. Hello, is it clear now? Hello, can I continue or stop? Hello, is it clear? Is it clear? Is it appearing, students? Oh, from the farad. Where is the farad? So much I explained it, na? Okay, let us see here. I will try for the 5 minutes. If problem will continue, then we will close. Otherwise, we will continue. Continue, then we will close. Otherwise, we will continue. Okay. Right. Let us see the capacitance of isolated sphere. Capacitance of isolated sphere. How we can derive? Hello, is it clear? Right, I think it is now clear. Capacitance of isolated sphere. How we can find out the capacitance of a sphere? For example, this is a sphere. You see this? This is a sphere. The sphere has a charge Q. Q is the charge stored on the sphere. Q is the charge stored on a sphere. Okay. And this sphere radius we can consider as the capital R. Right. I want the capacitance of this sphere. We know that the potential on surface of sphere. What is the formula for the potential on surface of sphere? The potential formula we know is 1 by 4 pi epsilon naught into Q by R. Is it correct? The potential on surface of the sphere formula is, we know that 1 by 4 pi epsilon naught into Q by R. Now, let us see. From this, we can write the amount of charge stored on the capacitor. Right? What is that? 4 pi epsilon naught R into, we can write as V. But we know I want the capacitance of this sphere which can store the charge. Right? Capacitance of sphere I want. Then what is the basic formula for the capacitance? The capacitance basic formula is amount of charge by potential. Right now? Amount of charge by potential is what? Potential formula is 4 pi epsilon naught R into V. Sorry. Charge by potential. Okay, charge we know, charge formula. This is equation 1. From equation 1 we write the charge formula, that is 4 pi epsilon naught R into V we can write by, or otherwise directly we can use the potential formula, right? This is the potential formula, equation 1. Okay, I want the capacitance of capacitor, right? Capacitance of capacitor. What is the formula for the capacitance of capacitor? Right, capacitance of capacitor formula is C is equal to Q by V. Now V formula we can write it here. That is, the V formula is 1 by 4 pi epsilon naught into Q by R. Right, and here Q gets cancelled. This denominator will goes to numerator and we will get the 4 pi epsilon naught into R. This is the formula for the capacitance of isolated sphere. Isolated means what? Single sphere, right? Okay, this is the formula for the capacitance of isolated sphere. From this, the capacitance does not depends upon the charge and potential. It will depends upon only radius, right? The capacitance depends upon radius of the sphere. Okay, right. And now let us see how to find out the capacitance of Earth. I want to find out the capacitance of Earth. Earth can also store the charge. If I want to find out the capacitance of Earth, then how we can find out the capacitance of Earth? In order to find the capacitance of Earth, we have to write the value of radius of Earth. What is the value of radius of Earth? Radius of Earth is the 6,400 kilometers. This you convert into meters. That is the 6,400 into 10 to the power of 3 meters. And we can also write the 1 by 4 pi epsilon naught value. What is the value of 1 by 4 pi epsilon naught value? That is 9 into 10 to the power of 9. And then from this we can also write the value of 4 pi epsilon naught. 4 pi epsilon naught value is 1 by 9 into 10 to the power of 9. Then capacitance of Earth I want to find out. Earth is a sphere. Earth is in spherical shape. We can give the charge for the capacitor also. It is a huge reservoir of the charge. It can store so much charge, right? Then the capacitance of Earth we can write like this. 4 pi epsilon value is 1 by 9 into 10 to the power of 9. And the radius of the Earth we can write as the 6,400 into 10 to the power of 3 meters. Now we can simplify it. If you simplify this, we will get the 711 into 10 to the power of minus 6 farads. Then we can write as 711 in microfarad we can write. This is the 10 to the power of minus 6 we write as micro, and this is the capacitance of earth. Students, is it clear now? Is it appearing clearly? Is it clear? Okay, then let us continue. This is most important, and now I am going to start very important topic, that is the capacitance of. There are three types of capacitors are there. Okay, capacitors are three types. How many types? Capacitors are three types that we are using in electronic circuit, right? Capacitors are three types. What are they? Right, the first one is the parallel plate capacitor. That means two plates are parallel to each other, parallel plate capacitor. And the second one is the cylindrical capacitor, cylindrical capacitor. Third one is the spherical capacitor. These are the three types of capacitors, but in our syllabus we have only one type of capacitor, that is the parallel plate capacitor. Okay, that parallel plate capacitor I am going to explain. Very important, and for the board exam, that very important, that I am going to explain. Three formulas I will explain, and out of that one derivation will come in the exam. That is, the first one is the capacitance of parallel plate capacitor, capacitance of parallel plate capacitor with without dielectric, or with air as dielectric. Okay, right. If there is no dielectric means non-conducting substance, right? If you have any query, write in the chat box. Clear? Okay, thank you. Anish replied. Okay, Suraj replied. Right, clear. Okay, let us continue. Then this is the first plate. This is the first metal plate, and this is the second metal plate. These are the two metal plates, and the first metal plate is connected to battery positive terminal, and the second one is connected to the battery negative terminal. Okay, these two plates are separated by small distance that we can consider as the d. Between the plates there is some gap is there. In that gap air is there. There is air. Dielectric constant is 1. Okay, and here this plate is the positively charged plate because it is connected to positive terminal of battery. This is the negative charged plate, and the area of each plate we can consider as the capital A, and the separation between the two plates is d, and electric field will be there. Electric field is from positive to negative, that we know very well, right? Now students, electric field is positive to negative, we know very well. I want the electric field formula due to this plate. Okay, electric field. Now electric field in between the capacitor has two plates. Okay, plate area is A, and separation between the two plates is D. These two plates are parallel to each other. That's why it is said to be parallel plate capacitor. Capacitor can be store the charge. It is storing the plus Q charge, and it is storing the minus Q charge. The amount of charge stored on the capacitor we can take as charge on any one plate. That is, we can take as the charge is Q. Okay, on one plate plus Q charge will be there, on another plate minus Q charge is there, but total charge is 0, but we cannot take total charge as 0. Then the charge on capacitor is equal to Q. Q is the charge on capacitor. Okay, Q is the charge on capacitor. A is the area of plate, area of each plate of capacitor. Okay, A is the area of each plate of capacitor, and D is the separation between the plates, separation between two plates. Right, I want the electric field between the two plates. How to find out the electric field between the two plates? Electric field between the two plates formula will be there, right? Electric field due to this positive plate will be there. For example, if any positive charged plate is there, Due to this positive charged plate at a distance some r, electric field formula you know. Electric field formula is sigma by 2 epsilon naught. Right? Here negative charged plate is there. Due to negative charged plate, electric field is also downward. Due to positive charged plate, electric field is downward away from positive charge. Due to negative charged plate is also electric field is downward. Right? Totally, the total electric field will be like this there. That is electric field due to positive charged plate plus electric field due to negative charged plate. We can write as electric field due to positive charged plate is sigma by 2 epsilon naught, and due to negative charged plate also sigma by 2 epsilon naught. Totally we will get as sigma by epsilon naught. Okay, this is the electric field. I want the potential difference between two plates of capacitor. Okay, I want the potential difference between two plates of capacitor. First of all, we have to calculate the electric field. Later, we have to calculate the potential difference. What is sigma? Surface charge density. Surface charge density means what? Charge by surface area. Charge by surface area we have to write. Okay, right. And here, potential difference between the plates I want. Potential difference between the two plates of capacitor. Okay, that is potential difference formula. We know, right? Electric field intensity is equal to dV by dr. This potential difference by distance. I am considering the potential difference between the two plate size d and the distance between the two plate size d. Then we can write as E is equal to V by d. From that V is equal to we write as Ed. Right? And E formula we can substitute it here. That is Q by epsilon naught A into dV. Right? This is the potential difference formula. Okay, understood. If you have any query, write in the chat box. This is equation 2. Right, now I want the capacitance of capacitor. First I calculated the electric field. Okay, first I calculated the electric field. Electric field due to positive plate. Okay, if you want I will clearly draw the diagram. I will indicate the electric field due to positive and negative plate. Due to positive plate, electric field is downward, right? That is E1. Okay, due to negative plate also electric field is downward, that is 2. Then the total electric field is also downward. The total electric field is E1 plus E2, that we got as sigma by epsilon naught Q by epsilon naught A. Then after finding the electric field, I find out the potential difference between the two plates. Potential difference between the two plates is Ed. E is the electric field and D is the separation between the plates. E we got in above equation. And then after that I want the capacitance of capacitor. Then how to find out the capacitance of capacitor? There is a formula for the capacitance of capacitor, right? What is that? The capacitance of capacitor basic formula is, right? You know very well the capacitance of capacitor basic formula is C is equal to Q by V, right? Q by V. V we can write here in this formula. V formula is, in the next step we will write. The C is equal to Q by V. From equation 2 we write V formula, that is Q by epsilon naught A into D, and here Q gets cancelled. This epsilon naught A goes to the numerator, then we will get a C is equal to epsilon naught A by D, right? Then finally we got as C is equal to epsilon naught A by D. This is the formula for the capacitance of capacitor. Okay, right, this is equation 3. Right, from this we say that the capacitance of capacitor depends upon area of each plate, and the capacitance of capacitor inversely proportional to the distance between two plates. These are the factors on which the capacitance depends. Okay, clear students? Any doubt in this? If you any doubt, you can write in the chat box. This is very important for the 3 marks. Very important for the 3 marks. Many times it came in the CBSE exam. Okay, right. This is the with air is dielectric. Without dielectric means there is no dielectric substance. There is no dielectric substance. Okay, and with air is air is present in between the two plates. Okay, students. Right. Let us go for the next concept. If you have any query, write in the chat box. Right. Now, second point is that capacitance of capacitance of a capacitor which is completely filled with a dielectric of dielectric constant. Okay. Okay. Next, I am going to derive the formula for the capacitance of capacitor with dielectric. With dielectric. Okay. For example, we see this is the first plate. This is a capacitor. Okay. And this is the second plate. This is the parallel plate capacitor. Capacitance of which capacitor it is? Capacitance of parallel plate capacitor. Capacitance of parallel plate capacitor. Parallel plate. Parallel plate capacitor. Okay. Parallel plate capacitor. And here this is connected to positive terminal and this is connected to negative terminal. Very important derivation. Remember it. Okay. The space between the plates is completely filled with a dielectric. This is the space between the plates. This is completely filled with the dielectric. Dielectric means what? Non-conducting substance. What is the need to fill with the dielectric? To increase the capacitance. Right? If it is filled with the dielectric, then the capacitance will be increases. The area of each plate we can consider as A, and this is the it is connected. This plate is connected to positive terminal, and this plate is connected to negative terminal. Right? And this is the dielectric. Dielectric we can consider as the glass or anything. Right? Whose dielectric constant we can consider as the K. And I want the electric field in between the two plates of capacitor we can consider as the E. I want the electric field. Right? Electric field in between the two plates of capacitor. First we can similar derivation will be there. Okay. Electric field in between two plates of capacitor. What is the formula for the electric field in between two plates of capacitor? Right? What is the formula for the electric field? Electric field same will be there. Right? Previously we derived sigma by epsilon plus sigma by 2 epsilon. This is the electric field due to positive plate downward will be there. Due to negative plate also downward will be there. Electric field due to positive plate away from positive downward will be there. Electric field due to negative plate away towards negative will be there. That is also downward. Is it right? Okay, students. Suraj and Anish and replied that clear. Okay, good. Let us continue. Very important topic that I am going to explain. Electric field in between the two plates of capacitor is that is electric field due to first plate and electric field due to second plate. Due to charged plate, this electric field due to one charged plate. You know that formula is sigma by 2 epsilon naught, na? Right? Here we write sigma by 2 epsilon naught, but dielectric is there, na? That's why we write is like this. Sigma by 2 epsilon we write. Instead of epsilon naught we write sigma by 2 epsilon. Here when we add both of them we will get as epsilon. Why we are writing epsilon? Because in medium permittivity is epsilon will be there. If the free space or air is there means the permittivity is epsilon we have to write. Here we write as sigma is q by a, and epsilon we write as k epsilon naught, and sigma we write as q by a. This we can consider as equation 1. And electric field we got. Next potential difference I want. Potential difference between the plates. Okay, what is the formula for the potential difference? Previously we derived after finding the electric field. Potential difference between two plates. Potential difference between two plates is V is equal to, we have formula that is electric field intensity into D. Electric field intensity we got is Q by K epsilon naught A. Okay, why we are taking the epsilon? Because it is in the medium. Dielectric is there. Without dielectric we write only epsilon naught, but with dielectric we have to write. Previously once you see, this is there is no dielectric in this. Here we wrote epsilon naught. But if the dielectric is there means non-conducting substance is there means if medium is there, then we have to write as like this. If medium is there, then we write epsilon. Okay, right. Next here we have to write E into D. From equation 1, E formula this one, and D. Potential difference we got here. Next I want the capacitance. Capacitance. Capacitance of capacitor with dielectric. Right? Capacitance of capacitor with dielectric. With dielectric. Right? With dielectric formula. Without dielectric previously we did out. Capacitance formula is what? C is equal to Q by V. Here we write Q by V is what? V is the Q by K epsilon naught A into D we write. Here QQ gets cancelled. Then what you will get? K epsilon naught A by D we will get. Right? And C final formula what you got? Right? K epsilon naught A by D we got. Okay? Right. With the dielectric, what you got? Without dielectric, we got epsilon naught A by D, capacitance formula. Without dielectric, with air is in between two plates, air is there, epsilon naught A by D. If dielectric substance is there, then the capacitance become K epsilon naught A by D. That means capacitance become K times. Okay, if a dielectric substance is kept in between the two plates of capacitor, okay, if any dielectric substance kept in between the two plates of capacitor, then its capacitance become K times. Capacitance of a capacitor. Capacitance of a capacitor becomes K times when a dielectric kept in between two plates of capacitor. In between two plates of capacitor. Okay, if we introduce a dielectric substance, the capacitance become K times. Okay, right. And let us see some note point I will give. That is in the note. This is a little note. Okay, let us see. First formula that we derived as capacitance of capacitor. Capacitance of parallel plate capacitor. Capacitance of parallel plate capacitor. Capacitance of parallel plate capacitor with air in between plates of capacitor. Okay, that formula is C is equal to epsilon naught A by D. This is the capacitance of parallel plate capacitor with air. With air. Okay. And the second point is that with completely filled with dielectric. Capacitance of a capacitor. Capacitance of parallel plate capacitor. Parallel plate capacitor. When a dielectric substance, when a dielectric substance is completely filled, when a dielectric substance is completely filled between two plates, right? If the dielectric is completely filled between the two plates, here there is no dielectric, this is the positive plate and this is the negative plate, no dielectric. Here air is there, right? This is the positive plate and this is the negative plate. Here what I am doing, that this is the positive plate and this is the negative plate. Between them I am introducing some dielectric, right? Then at that moment the capacitance formula is, we can consider the C dash, right? Its formula is we got as K epsilon naught A by D. that is K into epsilon naught A by D is the capacitance with air, right? If that means capacitance become K times, right? Okay, and the next one more 5 minutes I will find, not 5, 10 minutes I will continue, right? And one more capacitance formula we will derive, okay? And that is the capacitance of parallel plate capacitor. Capacitance of parallel plate capacitor when a dielectric substance of thickness T is introduced between the plates. Okay, here we are introducing the dielectric slab whose thickness is T, not okay. How it will be there? Let us see the diagram, right? This is the first plate, and this is the second plate. Every capacitor has the two plates. This is connected to positive terminal, this is connected to negative terminal, and this is the positive plate plus charge. On this we can consider the plus q charge, and this is the minus q charge. Okay, the separation between the two plates we can consider as the D. Now what I am doing, previously with air-raised dielectric without any substance in between the two plates of capacitor, we derived the formula for the capacitance. Now you see here, between the two plates, firstly I derived without any dielectric, I derived the formula, that is epsilon naught A by D. When space between the plates is completely filled with the dielectric, then the capacitance formula I derived K epsilon naught A by D. Now the capacitance formula I am going to derive, but the dielectric is partially filled. That means now let us consider this is a dielectric, right? The dielectric thickness is T. This is the dielectric substance. Okay, the thickness of the dielectric substance is T. This much partially filled. Now it is a partially filled. This case is that partially filled, not completely. Okay, without dielectric we derived, completely filled with the dielectric we derived. Now partially filled with the dielectric, right? Little amount of space is there for the air. Here air is there, here air is there, here dielectric is there, non-conducting substance, right? In this case what happens, right? Here electric field I want in air, this is air, right? Okay, and this is also air. Here it is dielectric, right? This is the dielectric, and here in the air the electric field I am considering as E1. In dielectric I am considering the electric field as E2, right? We will write the formula for the electric fields in air. First I want to write the electric field in air. Electric field previously in air we derived na, that is E1 plus E2 sigma by 2 epsilon naught plus sigma by 2 epsilon naught, that is we got as sigma by epsilon naught. Is it right now? Sigma by epsilon naught, and that we write as sigma is q by a, we write as q by epsilon naught a. This is in air electric field, that is E1. I want the electric field in dielectric. Okay, in dielectric electric field I am considering as E2. Okay, in dielectric electric field is E2. Then in dielectric means instead of epsilon naught we have to take epsilon, right? Actually two are there. Okay, electric field formula is sigma by 2 epsilon naught plus sigma by 2 epsilon naught, like that it will be there. Instead of epsilon naught here we have to take epsilon, and sigma we write as q by a, we write as epsilon naught a. Okay, E1 we got, E2 we got. E2 we write as epsilon we write as k epsilon naught, sigma we write as q by a, right? This is the difference. I want the next potential difference between the plates. Potential difference between two plates. Okay, how to find out the potential difference? Okay, it is very important. Potential difference we can find directly if previously in the previous derivation, right? And completely dielectric is there means we derive here there is little amount air is there, little amount dielectric is there, right? At that moment how we can derive, right? The potential difference we write is v1 plus v2 we write, v1 plus v2 we can write. Okay, within 5 minutes I am going to close. Don't worry, you remember it. Very important topic I am going to explain. I am covering the so little more syllabus. Okay, I'm going to. I'm not going to continue the next classes. Okay, you can watch previous lectures, and I will take rest for the more 1 week without classes. Okay, and today is the last class, and tomorrow onwards I will not take the classes. Okay, right. V1 is the potential difference between the plates. Potential difference what we write? Potential difference is the potential difference between the plates. For example, potential difference two types is there here. Little amount of air is there. In air medium we write the potential difference V1. In the dielectric we can take the potential difference as V2. Okay. What is the formula for the potential difference generally? Potential difference formula is, you know, that V is equal to ED, right? Previously we derived. Actually, electric field formula we know E is Vd, V by D, electric field between the plates. Formula is potential difference by distance. From this, potential difference is equal to electric field into distance. Right here, potential difference in air. Field in air we have to take potential difference equal to electric field into distance. Potential difference in air means electric field in air, that is E1, and to distance in air. In air, distance is what? Right in the short box. This part is air, this part is air. This is dielectric. Right, from the total you remove the air part. Air distance is d minus t will be there. D is the total separation. In the dielectric only air thickness. Then you remove the dielectric thickness, you will get the air thickness. Next, potential difference in the dielectric. In the dielectric electric field we have to take. In the dielectric thickness we have to take dielectric separation. D is the distance, no? Distance in dielectric we have to take. Dielectric distance is t. Now here we got the equation. Then now electric field formulas you substitute in this. Electric field formulas use A into D minus T. E2 is Q by K epsilon naught A into T we write. And here we can common the Q by epsilon naught A. When we common the Q by epsilon naught A from this, we will get as T minus T will be remains here. Here Q by epsilon will be remains, means here T by K will be remains. This is the formula for the potential difference. Next I want the capacitance. Capacitance of capacitor. Capacitance of capacitor. How we write the capacitance of capacitor? Right, the capacitance basic formula is what? C is equal to, we have the Q by V. Right, by V. Right, this formula we have to use it here. Now you take the screenshot. Right, you take the screenshot and its continuation I am going to do now. Right, okay, let us see here its continuation. And Q by V what you got here? C is equal to Q by V. You got potential difference in the previous case we derived. Just okay, what is the potential difference? Just I will scroll down. You see, this is the potential difference that you got. And now we can simplify and we write in this. And the potential difference we got is what I got. What we got? Once we Q by epsilon naught A, something we got. Right. Q by epsilon naught A into T minus T plus T by K. This we got. Now QQ gets cancelled. Then the capacitance we got as epsilon naught A goes to numerator. Epsilon naught A by T minus T plus T by K.